All right, so we're going to finish up section 6.2. So we'll keep looking at the unit circle trig. And remember, the most important thing you need to do unit circle trig is the what? Coordinate. You need the coordinate. So if I give you an angle to work with and you want to do the unit circle trig, you've got to figure out the coordinate. So we did 45. And what was the coordinate for a 45-degree angle? Yep.
Square root of 2 over 2, square root of 2.
Yep, square root of 2 over 2, square root of 2 over 2. Now we're going to look at the coordinates for 30 and 60. And once you know the 30, you automatically know the 60. They go together. Because if you look at the 30 and the 60, they're the same triangle. The only difference is which way it's kind of rotated. Right. So let's see if we can figure out the 30. Okay, let's do that one. Okay, so I've taken the triangle that I have in the circle. I've drawn it off to the side a little bit bigger. Okay, I've got the 30, 90, and at the top would be my 60 because all the angles have to add up to 180. Is there any side in that triangle that we know the length of right now? Yeah.
The bottom of the 30-degree triangle is 1.
The bottom of the 30 is 1?
No, the triangle.
I don't think we know anything about the bottom. If we did, we'd already know the coordinate, the x value for the 30. There is something we know, yeah?
Would the one that's going vertically, would that be like, would that be like 5 or something?
Maybe. We don't know that yet. But there is something we know. What length? What side do we know the length of in the 30, 60, 90? Yeah.
Is the terminal side 1?
Yeah. How come we know that? The hypotenuse there is 1. How come?
Because the unit circle, the radius equals 1.
Yeah, it's a unit circle, and because the hypotenuse is the radius of the circle, this side is 1. Now, when we found the other two sides, we labeled them x. I think we used like x and x yesterday. Can I use the same letters for the base and the height of the 30, 60, 90? Why not?
Because they're not the same length.
They're not the same. So the problem is, if we try to do Pythagorean theorem right now, we'd have to label one side x, one side y, but then you can't solve that, because you'd have x squared plus y squared equals 1 squared. So we still need to use Pythagorean theorem, but we need to figure out another side first, a different way. Yep.
Would it be x and 2x or no?
There is a connection between them, but not quite. Yeah, there is a connection. If you do know the 30, 60, 90 right triangle from geometry, you could figure it out. But we'll pretend we don't know it. Okay, and we'll figure this out without relying on anything we might have to have already memorized. So my suggestion to figure this out is to take this and make a copy of it. Okay. So any thoughts of what I can do with that? Yep, Julia.
I'm just thinking of this randomly. Could you solve it like you would solve a rectangle and then clockwise or no?
So make it into a
rectangle.
You could make it into a rectangle. I'm not sure how we would solve it if we put those two triangles together and made them a rectangle. But you could. But I don't know what you would do from there. Yeah, go on.
Flip it, and then both sides be the same.
All right. So you want to take this one and flip it?
Yeah.
How do you want to flip it?
The y-axis.
Flip it over the y-axis?
Yes.
So, like that?
Yeah.
Okay. And then what would you do with that?
Then you put it on the y-axis.
Okay, we can move that.
You get a bigger triangle, but
We would get a bigger triangle.
but all the sides are
Yep, two of the sides are the same. It is isosceles. I'm not sure though, because we got to figure out this side or this side. We need one of them. How would we get either one of those sides from that picture? Yeah, I'm not sure, but we're on the right track here. Yeah.
If we flip it over the x-axis, wouldn't all angles be equal to 60? And then each side would equal one another?
All right, so if we flip it over the x-axis, we can put them together like that. And then, what did you tell me is going on here now?
No, all angles are 60 degrees, so
Yeah,
each
so yeah.
angle is 1.
60, 60, 60. So we have an equilateral triangle, which tells us that this side over here is 1 unit from there to there. So what do we know about the length of that purple segment and the length of that blue segment? Yeah.
They both are equal, and they both add up to 1.
Yeah, they're equal because they're reflections of each other. So if they're equal and they add up to 1, there's only one thing they could be. So what does it mean that it has to be? Yeah,
0.5.
0.5 or a half. So now we just figured out one of the sides in the triangle without using Pythagorean theorem. We can finish it off with Pythagorean theorem. Okay, we don't need the bottom triangle anymore. Okay, so if we want to move, I mean, you can leave it or you can move it, but that's what we need. Okay, what could we call the bottom side now? Sure, let's call it x. And what would be the formula that we could set up to solve for x? Yeah.
1 squared equals 1/2 squared plus x.
Squared equals a half squared plus what?
X. X squared.
X squared. Okay, so 1 squared equals, what's a half squared?
0.25.
How much?
Is it 0.25?
Yeah, I'm just going to write it as a fraction, 1/4. Okay, what would we do next to get x by itself?
Subtract by 1/4 on each side.
Yep, and what would that give you on the left?
3/4.
3/4. Okay, so we have x squared equals 3/4, and what would our last step be?
Square root each side.
Square root each side. We got to take the square root of the top and the bottom separate. So square root 3 over square root 4 equals x. And square root of 3, does that simplify? Nope. How about square root of 4?
Yes.
Yeah. What does that simplify to? 2. So square root 3 over 2. If you remember, we saw that number yesterday. Square root 3 over 2, that's where it comes from. So now the bottom side is root 3 over 2. So we know the length of the bottom, and we know the height of the 30, 60, 90 triangle. So what would be the coordinate for 30 degrees? Yeah, root 3 over 2, comma, 1/2. That's the coordinate for 30 degrees. That's how far over you go on the bottom, root 3 over 2. And then the height of the triangle is how far up you go, and that's 1/2. Now that we know the 30, we don't have to redo it all for the 60. 30 and 60 are the same triangle, it's just one's rotated standing up, and the other one's kind of with the long side laying down. So what do you think the coordinate for the 60 is? Yeah.
Just use flip the x and the y.
Okay, so it would be
1/2 and then square root 3 divided by 2.
1/2 root 3 over 2. Yeah. So that's the coordinates for the 30 and the 60. Any question on those two? So now we know the coordinate for 45, the 30, and the 60. Let's try doing a few trig functions, but we don't want to have to figure those out again. So we just want to memorize those are the coordinates. Now, if you can mix these up easily, right? They're both 1/2 root 3 over 2, but you do need to get them in the right order. Which number is bigger, root 3 over 2 or 1/2?
Square root of 3 over 2.
So the square root of 3 is about 1.7. So which one is bigger? Yeah.
Square root of 3 over 2.
Yeah, square root of 3 over 2 is about 0.86. 1/2 is 0.5. So if you forget which one goes where, think of your triangle. This is the 30. This is the short side. The short side in a 30, 60, 90 is always the 1/2 because it's the small number. The long side is always the root 3 over 2 because it's the big number.
You said closer to 1.7.
The square root of 3 is about 1.7.
Then what would the coordinate of 0 be?
A 0-degree angle?
Yeah.
That would be 1, 0. Yes.
How, sorry.
Yeah.
So for the 1/2 on the triangle, how do you get the 1/2 again?
The 1/2? That came from kind of just doing a clever trick where we made a copy of the triangle, duplicated it, and flipped it.
Oh, yeah.
Yeah,
Thank you.
that's where the 1/2 came from. So it was just a clever trick to figure out the 1/2. Yep.
Are we finding the coordinates for 60 degrees and 30 degrees?
Yes, that's what we just
So
found.
once we have those are going to stay the same.
Correct.
So we can put that on like our reference sheet.
Yeah.
Okay, perfect.
So square root of 3 over 2's length's 1.7, but then if you...
Square root 3 over 2 is about 0.866.
0.86, okay, that's fine. Okay.
Yeah. Root 3 is 1.7 roughly.
3 is... Okay, that
Yeah.
makes more sense.
Yes.
On the test, for like finding the sine, cosine, and tangent, is it just going to be like 30, 60, 90 degrees, or are you going to be like 65, like 95? Is it going to be like more specific?
There will be up to 16 different points. So we've done the 4 quadrantal angles, and then we've done 5, 6, and 7. So we've done 7. So we've got a few more to look at. But they're all going to be multiples of 30 and 60. So once you know these coordinates, there are no other coordinates we have to figure out again from scratch, like we did here. We can reuse all of the stuff we've already done. All right, so let's try a few trig functions. Okay. Find the 6 trig functions of 45 degrees. Okay, so they gave us 45 degrees. That's fine that they give us an angle, but we really need the coordinate. What is the coordinate for 45 degrees? Yeah.
Is it square root 2 over 2, square root 2 over 2?
Yep. Square root 2 over 2, square root 2 over 2. Now we've got the coordinate. We can go through and find all the 6 functions. What's the sine of 45 degrees?
Square root 2 over 2.
Yep. What's the cosine of 45 degrees?
Square root 2 over 2.
It's also root 2 over 2. Okay, this is looking similar to what we did in the homework last night, because that's what this one was. What about the tangent?
Yeah. 1.
1, because you're dividing 2 things that are the same. How about the cosecant of 45? No, the only undefined ones can have to be multiples of 9.
Wait. No, I'm like. Okay, don't go back.
Yeah.
Square root of 2.
Square root of 2. Yep. So when you flip root 2 over 2, you get root 2. I think that's the one that someone had asked me about earlier. Yep. How about the secant of 45? It's also square root of 2 because the sine and cosine are the same.
Square root of 2, because on the homework I got 2 square root 2.
It would be 2 square root 2 over 2 when you fix it.
Oh.
But then the 2's cancel.
Oh, right. Oh, so that's, oh. Do we, like, because you divide the 2? Or they just cancel?
They can't, yeah, because they're division. Yeah, it cancels
Okay.
out.
Thank you.
Yep. And then what about the cotangent of 45? Yep. 1.
It's good, we just repeated it.
Yeah. So that's the 6 trig functions of 45 degrees. So whenever you're dealing with a multiple of 45, you should be thinking in your head the coordinate is a root 2 over 2, root 2 over 2. When you're dealing with a 30 or a 60, you should be thinking of the two numbers 1/2 root 3 over 2. But you got to get them in the right order. So let's draw the 30 and figure it out. Pretend like we can't remember the order of which one goes where. So 30 would be right about there. Okay, it's lower towards the x-axis. If you make a triangle, there's my 30, 60, 90 triangle. Where is the long side there? Yeah, the long side is the x. And what is the length of the long side always in a 30, 60, 90? Yeah?
1.
That's the hypotenuse. But this is the long leg. Yeah.
The square root of 3 over 2.
Square root 3 over 2. And where's the short side? Yep.
The Y.
The y. Okay, that's the short side. And how long is the short side in a 30, 60, 90? It's always 1/2. So now we know the coordinate is root 3 over 2, 1/2 from the picture. Is there any question how I used the picture to figure that out? If it was the 60, it would have been the opposite. The short side would have been on the bottom, and the tall side would have been the y. Okay. But this one we do want root 3 over 2, 1/2. All right, so we'll go through all the trig functions. What is the sine of 30 degrees? Yeah. Yeah, 1/2. What's the cosine of 30 degrees? Yeah.
Square root 3 over 2.
Square root 3 over 2. Okay. And the tangent, we have to divide the y by the x. So just imagine putting a division line right there. What's going to happen when you divide the y by the x? Yeah?
Square root of 3 over 2 is going to flip.
So you would flip and multiply, and then what would cancel out? The 2's, yeah. So when you divide the y by the x, the 2's are going to cancel out, and you would have a 1 in the top, and you would have a square root of 3 in the bottom. But we can't leave the square root of 3 in the bottom like that. So how do we, or can you just tell me what you get when you fix it? Yeah.
I had a question. I was wondering how the 2 cancel out.
Um,
It was 1/2, so I
yeah.
got 1. That makes sense.
Because when you flip and multiply, those cancel, and then you get 1 over the square root of 3.
Didn't you multiply by square root 3 over square root 3?
Yep. And what do you get when you multiply by root 3 over root 3?
You just get root. No, you get root 3 over 3.
Yes. Okay. And there's your tangent, root 3 over 3. All
And
right.
are we gonna, is on the test, is there gonna be ones where we have to find the coordinates for like 45 degrees, or as long as we remember them, then just in case we don't?
You'll have to figure out the coordinates somehow. It's probably best if you can just remember it. Yeah.
So if we just remember it, we won't have to like do them all out?
No.
Oh, okay.
How about the cosecant of 30 degrees? Yep. 2. And how about the secant of 30? What would that be? Yep.
2 square root 3 over 3.
Yep, so when you flip this, the root goes to the bottom, but then you have to fix it. and you end up with 2 root 3 over 3. And now for the cotangent, you could flip either one of these. I would flip the first one, because when you flip that, you're done. If you flip the second one, then you have to fix it again. So what's the cotangent of 30 degrees? Yep.
Root 3.
Root 3. Yep. So that's the 6 trig functions of 30 degrees. Yes.
Can you go over how you got the cosecant?
Cosecant, we flip the sign. So when you flip 1/2, you get 2.
Yeah.
Okay, so that's the 30. Now let's look at the 6 trig functions of pi over 3. What's pi over 3? Yep. 60 degrees. Okay, so now when we think of our sketch, okay, we know it's a multiple of 30, right? 60 is a multiple of 30, but 60 degrees is higher on the circle. So when you make a triangle, the short side is at the bottom, and the height is the tall side. Okay, so 1/2 root 3 over 2. So you're going to get all the same values we just did in the last problem. But since the x and y switch, all the answers are going to switch places. What's going to be the sine of pi over 3? Yeah. Root 3 over 2. What about the cosine of pi over 3? Yeah.
1/2.
Yep, 1/2. And for the tangent, again, just imagine putting a division line right there and divide those two answers. What's going to happen when you take root 3 over 2 and divide by 1/2? Yeah.
Hager or the halves, so it would be root 3.
Would just be root 3. The 2's would cancel out. Okay, so we got that. What about the cosecant of pi over 3? Yeah.
Square root, 2 square root 3.
2 square root of 3. A little more to it. Yep.
Divided by 3.
Yeah, so it's going to be 2 root 3 over 3. Okay, how about the secant of pi over 3? Yeah, 2. And what about the cotangent of pi over 3? Yep, square root of 3 over 3. So if you compare all the answers that we just got in the last two problems, they're all the same answers. Every 30 and 60 has these answers. It's just they move around in different spots because the 30 and 60 have the x and the y switched. They're all the same answers. Yep.
Can you show how you got the 2 square root of 2 over 3?
So when you flip root 3 over 2, you get that. And then when you multiply top and bottom by root 3, you get 2 root 3 over root 9, which is straight. All right, so that's working with the 30, the 60, and the 45. Well, if we can work with those, we can do 135 as well. Very easily. Think about, is it working? Oh, did you? So find the trig functions listed above 135. So think about 135. Okay, 135. Is that a multiple of 30 or is it a multiple of 45? That's a multiple of 45, yes. So think about where it would be. Here's 0. Here's 90. Here's is 180. Where would 135 be? Yeah.
Halfway between 180 and 90.
Yeah, it's halfway between 90 and 180. So it's a 45, 45, 90 triangle. Right there. We already have a 45, 45, 90 here. It's a reflection of it. So when we're dealing with 135, we already know the numbers we need to use. It's just because it's in quadrant 2, one of the coordinates has a negative on it. So anyone think they know what the coordinate is for 135? Yeah.
Would it be the square root of 2 over 2, square root of 2 over 2?
That's 45. That's right here. Square root 2 over 2, square root 2 over 2. No, we don't want to do anything with adding or subtracting 360 right now. Yep.
Would it be negative square root of 2 over 2?
Yep, negative square root 2 over 2. And the y value? Yep. Root 2 over 2. So when you're working with a 45-degree angle in the other quadrants, the only difference is the x can be negative, the y can be negative, or both could be negative. But that's all that changes. So you can reflect the 45 down here. That would be 225. And you can reflect it down here. 315. Okay. So what's the sine of 135? Yeah.
Square root of 2 over 2.
Square root 2 over 2. What about the cosine of 135? Yeah.
Negative square root of 2.
Negative root 2 over 2. And what about the tangent of 135? Yeah. Yep, negative 1. So I didn't do all 6 trig functions. I only did 3. But that's, you know, as we start to do them, I'm not gonna keep doing all 6. Any questions on that? All right, let's try. Let's do one more of those. Let's do. Let's call it example 4B. Find the. Let's just do the sine. Find the sine of 315. Okay. So we got to first figure out what is it. Well, what do we have to find first about 315? Yep.
If it's multiple or not.
So what do we have to do in general for unit circle trig? We got to find the. Yep. Right. We need the coordinate. Right, now to figure out the coordinate, we want to figure out if that number is a multiple of 30 or 45. That's going to tell you if it uses the root 2 over 2's or if it uses the 1/2 root 3 over 2's. What is 315 a multiple of? Yep.
45.
It is a multiple of 45. And 315 is when you draw the 45, 45, 90 in quadrant 4. So what's the coordinate of 315? Yeah.
Positive and then negative square root over 2.
Yeah. So positive root 2 over 2, negative root 2 over 2, and now they just asked for one specific thing. That's how it'll be on the test. What's the sine of 315? Negative square root 2 over 2. Okay, so that's how you work with 45-degree angles in the other quadrants. Okay, now we're going to work with the 30s and the 60s in the other quadrants. That's the same thing. Okay, we know we got the 1/2 root 3 over 2. It's just sometimes they're going to be negative now. Okay, 7 pi over 6. Well, what's pi over 6?
30 degrees.
30 degrees. So this is 30 times 7. How much is that? Yeah.
30 times 7 is 210.
210. So let's make a sketch and see if we can figure out the coordinate for 210. Before I make the sketch, is 210 a multiple of 30 or 45?
30.
Yeah, because the way we got it was 30 times 7. So yes, it is a multiple of 30, which tells you it's going to use root 3 over 2s and 1/2. But we got to get the order right, and we got to get the positives and negatives right. So let's think about 210. Here's 180. Here's 270. Where's 210? Yeah.
Closer to the 180.
It's closer to the 180. Okay. It's maybe about right there. So make your triangle. Where's the short side? What direction does the short side go in on that triangle? Yeah.
Down.
So vertical or horizontal?
Vertically.
Yeah, it's vertical, but yeah, it does go down. But that side is a half a unit. And what about the long side? How long is that?
How do we know that it's a half a unit? Is that just always how it is?
In a 30, 60, 90, yeah.
Oh.
Yep. And what about our long side? Yep. That's the hypotenuse. When I say long side, I mean long leg.
Wait, but wouldn't it still be 1 since it's like flush to the x-axis?
Well, I didn't draw a good circle. My circle's not really a circle. It looks more like an oval. That's why it doesn't look good. Yeah.
Oh, it'll be root 3 over 2.
That's root 3 over 2. All right, so now we've got the long leg, the short leg, and now we just have to write the coordinate for 210. So what would be the coordinate for 210? Yeah.
Negative root 3 over 2. Negative 1/2.
Yep, negative root 3 over 2, because you got to go left, and negative 1/2 because you go down. Okay. So what's the sine of 7 pi over 6? Yeah. Negative 1/2. What's the cosine of 7 pi over 6? Yep.
Negative root over 2. Or root 3 over 2.
Negative root 3 over 2. And the tangent, again, just imagine putting a fraction line right there and dividing negative 1/2 by negative root 3 over 2. What's going to happen when you divide those two values? Yep.
Is the final answer going to be root 3 over 3?
So, yeah, so the negatives are going to cancel, the 2's are going to cancel, and you would have 1 over root 3. But you do need to fix it by multiplying top and bottom by root 3. That's the sine, cosine, and tangent of 7 pi over 6. Okay, any questions on that? All right, let's try. I think that's it. I could just make up one more. Let's do the cosine of 300. Okay. So what do we need to know about 300 first?
What it's a multiple of?
Right. And is that a multiple of 30 or 45? 30. So let's draw our diagram. 180, 270, 360. Where's 300? Yeah.
Between 270 and 360.
Right in the middle?
No, not right in the middle. It's closer to 270.
Closer to 270, yeah. So we're gonna put a point there that's a little bit after 270. Make your triangle. And if you draw it right, you should be able to tell that you have a long side and you have a short side. Okay. So the short side is right here. And what's the length of the short side? In this kind of triangle? Yep. It's always a half. And here's your long side. What's the length of the long side? Yeah. Square root of 3 over 2. So now you have enough information. What's the coordinate for 300 degrees? Yeah, River.
Negative square root of 3 over 2, 1/2.
That would put you up over here. In quadrant 2, there are negative and positives.
The opposite of what I just said.
Okay, so what would it be?
It would be 1/2 negative square root of 3 over 2.
Because we got to go right and we got to go down to get to 300. So right means positive, down means negative. And now they want the cosine. So what would be the cosine of 300? 1/2. Okay, so there's a lot of repetition, right? When we start looking at the 30s and 60s, we get all kind of the same answers over and over. So the diagram you can kind of think of now that you should be able to work with. You should be able to do these 4 angles. So that's the 0, 90, 180, 270. You should be able to do the 45s. So 45, 135, 225, and 315. And then you should also be able to do all the 30s and 60s. So you've got 30, 60. And then over here you've got 120, 150. You've got 210 and 240. And over here you've got 300 and 330. So those are all the different angles that we can work with on the unit circle. And everything is really just a reflection of the 3 in quadrant 1. That's all they are. You'll notice they are not equally spaced. We have some gaps in here. There's a gap here. We didn't talk about that one. And there's a gap here. Anybody know what those 2 ones in black would be? Yep.
15.
They'd be 15s. Okay, we are going to talk about the 15s, but not for a while. Okay. So for now, just the 30s, 45s, and 60s. Any questions on that? All right, so those are all the angles we can do on the unit circle. Well, what if we can't do it on the unit circle? If it's not a multiple of 30 or 45, then we'll use a calculator. So I'm going to show you how you type it in. It is important that you set the mode. There's a mode on the calculator for radians and degrees. You just have to look at the directions in the problem. Okay. So it says to find the 6 trig functions of 42 degrees. Is 42 a multiple of 30? Is 42 a multiple of 45? No. If it's not one of the angles in this chart, then for now, we're doing it on the calculator. All right. And what is it that they want me to find the 6 trig functions of in this problem? The 6 trig functions of what? 42 degrees. So that means when I use my calculator, it needs to be in degrees. Right, so when you turn your calculator on, it'll say the mode in the top row. It's one of the things it tells you. If it's not in degrees, if you press mode and then go to the 4th row down, you can pick degrees or radians. Again, I want to keep it in degrees, so I'm just going to leave it in degrees. All right, and all we have to do is do sine 42, cosine 42, and tangent 42.
Why can't we always just put it in the calculator?
What's up?
Why can't we just always put it in the calculator?
Because if we put it in and we're doing problems like cosine of 30, it's not going to tell us it's root 3 over 2. It's going to give us these decimals. So we always want to make sure we're getting the exact answer, not a decimal answer. But when you're doing something that's not a multiple of 30 or 45, it's not easy to get an exact answer. So decimals are okay for these problems. Okay, so there's the, just ignore this, that was extra. The sine, the cosine, and the tangent. Now, we don't have buttons that say CSC, SEC, and cotangent. We don't have buttons for those. So how do you think we're going to find the cosecant of 42 degrees?
Just get the reciprocal.
Yeah, just take the reciprocal. Same way we've been doing it all along. 1 divided by the sine. Okay. Don't do 1 divided by 0.67 because that's rounded. Do 1 divided by sine 42. That's the best accuracy we can get. Okay. And then how would we do the secant? What would I type in? Yep.
1 divided by cosine.
Yep, 1 divided by cosine. And how would I do the cotangent? Yep.
1 divided by tangent.
1 divided by tangent. Okay. So that's how you do the sine, cosine, tangent, secant, cosecant, cotangent on a calculator.
For like, say we're with the answer of secant, will we do 1.5 or do 1.5?
Secant, you would write, based on this, 1.35.
Oh no, you want to go. Sorry.
Cosecant, you would write 1.49.
Okay, so don't round to. Thank you.
So 0.67, 0.74, 0.90, 1.49, 1.35, 1.11. Rounded properly. Okay, let's try another one of those. This time they're only having us find 2 trig functions. What are they having us do this time?
Is it not working?
Yeah, I gotta fix it. That's okay. What do they want us to do this time? Yeah.
Find the trig functions of
10 what? 10
10
radians, yeah. There's no degree symbol on there. You need to know that that means radians. If you do it, if you leave your calculator in degrees and you do it, you're not going to get an error. You're going to get numbers, but they're all going to be wrong. So make sure you put it in radians. And now once you put it in radians, you do the same thing. So it should say, just trying to quit. It should say radians at the top. If it doesn't, it means you're still in degrees. Sine 10 and cosine 10. That's sine of 10 radians and cosine 10 radians. Okay. Any question on that one? So when we look at, let's go back here. There's a connection between this and this. If you know the sine, what do you do with it to get the cosecant? Yeah, you find the reciprocal. And if you know the cosine, what do you do with that to get the secant?
The reciprocal.
The reciprocal. Okay? These are what we call reciprocal identities. It's not that it only works if that's a 4 and that's a 2. It works all the time. You put any number you want in. 47, 56, negative 32.5. Anytime you flip the tangent, you will always get the cotangent. Anytime you flip the cosine, you will always get the secant. Right? And these are called reciprocal identities. And I've kind of written them twice, because what I'm saying here is if you flip the sine, you get the cosecant. But then if you flip the cosecant, you get the sine. It changes it back. If you flip the cosine, you get the secant. Flip the secant, you get the cosine. And notice I didn't fill in a specific number for this angle. I just left it as the angle, whatever the angle is, 42, 57, 10. That doesn't matter. It works all of the time. Okay, so these are what we call reciprocal identities. Now, earlier somebody mentioned something about adding and subtracting. Like if you have an angle that's too big to work with. Does anybody remember what we said earlier? You can add and subtract what to make it easier to think about? Yeah?
360.
Right, 360. So if you've got something in degrees, and let's say you wanted to do the sine of 780, that's what you get. Well, if you subtract 360 from it, 780 minus 360, that's the same thing. Right? Adding and subtracting 360 isn't going to change the answer that you get. So I've done the same problem 3 different times now. Sine 780, 780 minus 360, 780 plus 360. What's 360 the same as in radians? Yep.
2 pi.
2 pi. So if I switch over to radians, I can do the same thing now with 2 pi. Yeah. Let's take the sine of 5.
Don't close it.
Don't close it all the way.
Now let's take the sine of 5 plus 2 pi. Same thing. Adding 2 pi didn't make a difference. What if I add 2 pi twice? How much would that be? It would be 4 pi. It'd still be the same thing. Plus 6 pi, plus 8 pi, plus 10 pi. I can add and subtract 2 pi as many times as I want, and it will not change the answer. So that's it's actually the second thing I was going to mention. I'll go back to the first thing in a second. So when you have sine and cosine, if you take the sine or the cosine of a value, or you take that value and you add 2 pi to it, or 2 pi times 2, 2 pi times 3, 2 pi times 4, any multiple of 2 pi, it will not change the answer. Okay. The other thing I want to mention about sine and cosine is more how they look. They are connected. Okay, they look like a wave. We're going to study what they look like more later on. But that's what sine looks like. And you notice it doesn't go any higher than 1, and it doesn't go any lower than -1. Cosine looks very similar. It's a little bit different, but it's like a horizontal shift. Okay, it goes up to 1, goes down to -1. But it does go left and right forever.
No tangent.
These are the only 2 trig functions that have a domain of all real numbers. Every other trig function looks very different. Okay, if you look at tangent, there's a pattern to it. But the big difference is it's broken into pieces. Tangent is not a connected function. You have to lift your pencil up every time you want to draw the next section. Sine and cosine are the only 2 that you can just put your pencil down and just draw the whole thing. So no, tangent, cotangent, secant, cosecant, all are broken by vertical
What
asymptotes.
does it say on the calculator?
I don't think there's any, yeah, there's nothing there.
Is that a T or plus sign?
T. Yep, T plus. So that idea that you can add and subtract 2 pi as many times as you want, that's called the periodic property of sine and cosine. All right, so the last thing I'm going to show you, and I already showed you part of them, are two more identities. Okay, I've shown you what are called the reciprocal identities, where you flip sine, you get cosecant, you flip cosine, you get secant, and so on. And I want you to remember that because those formulas are identities, they are true all the time. It's not like they only work for odd numbers or even numbers, or no, they're identities. You always can flip the sign and get the cosecant. It doesn't matter what you plug in, it always works. So there are different groups of identities we're going to look at. The reciprocal ones are ones I already gave you. And I'm going to add 2 more to that list. And the 2 that I'm going to add, you already know what they are. If you think about what I've taught you with unit circle trig, you can figure them out. What is sine when we do unit circle trig? It's equal to what? Y. What's cosine? X. And what's tangent? Y over X. So what's another way you could write tangent? Yeah?
Sine over cos.
Yeah, sine over cosine. The tangent is equal to the sine divided by the cosine. I can easily show you with a number. If I just take the tangent of 14, or whatever, that's exactly the same as taking the sine of 14 and dividing by the cosine of 14. Sine divided by cosine will always give you tangent. What do you think cosine divided by sine will give you? Cotangent. Yeah. So again, notice we're getting away from filling in numbers here. Not actually filling in an angle, because these work all of the time. Okay, the goal is not to fill in an angle. And I'm going to show you what we do in a second. I'm not going to talk about that right now. All right, so let's see if we can use all the formulas on the left to simplify what's on the right. So the goal is to take an expression that has trig in it and try to make it simpler. We have cosecant times tangent. Okay, cosecant of what? Not anything. Okay, cosecant of an angle times the tangent of the angle. And I want to see, can you do that in a simpler way rather than doing cosecant times tangent? How can you rewrite cosecant? You can rewrite that as 1 over sine. And now I'm also looking for a way that I can rewrite tangent. Yep.
Sine over cosine.
You can rewrite tangent as sine over cosine. Okay, so all I've done so far is I just substituted in for cosecant and tangent the 2 formulas from the left side. What happens when you multiply straight across now? Yeah.
Yeah, signs cancel out.
Signs cancel out. And what are you left with? We're going to be left with a fraction, but what's going to be in the top? 1 is in the top, and what's in the bottom? Cosine. Now, 1 over cosine can be simplified even a little bit further. What is 1 over cosine? Yep. Secant. So if you had to take the cosecant of an angle and multiply by the tangent of an angle, the simpler way to do that is just take the secant and you'll be all done in one step. That's simplifying a trig identity. Any question on that one? All right, let's try another one. I think I got 2 more. Let's try secant times cosine. Okay, so my goal is to figure out, is there an easier way to do secant times cosine without doing secant times cosine? How can you rewrite secant? Yep. Yep. 1 over cosine. And you don't want to rewrite cosine. The goal is to rewrite things that are not sine and cosine. If something already is sine or cosine, just leave it. If you want to put it over 1, you could do something like that. But yeah, secant is 1 over cosine times cosine over 1. What happens there? And what do you get?
0.
What'd you get? No, you don't get 0. You get 1. And you should get 1 because you're multiplying 2 things that are reciprocals. That's like multiplying 3 and 1/3 or 5 and 1/5. If you multiply 2 things that are reciprocals of each other, which these are, you always get 1. So sometimes when you simplify a trig expression, it just turns into a number. Not most of the time. All right, and let's try this one. So anything that's not a sine or a cosine, change it so it is a sine or a cosine, and then the hope is something is going to cancel out. How can we rewrite cotangent? Yeah?
Cosine over sine.
Yep. Cosine over sine. And how can we rewrite cosecant? Yep.
1 over sine.
1 over sine. And now, how do we handle dividing a fraction by a fraction? Yep.
Don't the signs cancel?
Yeah, because you would flip and multiply, so the signs would cancel. And what are you left with? Cosine. Cosine over 1, which is just cosine. So if you needed to take the cotangent of an angle and divide by the cosecant of an angle, a simpler way to do that is just take the cosine and you're done in one step. Okay, so there won't be a lot of those on the test, but I would expect to at least see 1 or 2. Okay. Any questions on that? All right. Okay, so that is the homework, and I'm just going to make up a different simplified problem. Let's do So I want you to do problems that are on 335 and then simplify tangent times cosine. Okay, we've got just about 10 minutes, so I'm going to have enough time. I think I'll put all the lists of topics on the test. I'll put that in the video, and if you have any questions, you can ask me about it. Yeah.
Did you say the review this actually
I thought I did.
Okay, is that due to like
So yeah, if you do the review, that would be due tomorrow.
Okay.
Yep.
Is everything in the review going to be on the test?
Yes, the review should be a pretty accurate gauge of what's on the test, but I'm going to put a list of topics on the board right now.
And are you going to be
I think we won't get it